All right, AP students, welcome to your Redox review for Unit 9. This is covering Unit 4, foundational introductory info on Redox, and then leading us into our in-class lecture where we begin looking at the electrochemical cell. So, electrochemistry is the area of study in chemistry where we study the exchange of chemical and electrical energy. So Unit 9 tends to be a physics fan favorite out of all the units. Quick review from Unit 4. We call reactions that involve the transfer of electrons metathesis reactions. Single displacement, double displacement are often metathesis reactions. Not all synthesis, but some synthesis are. It's their own category of reactions, kind of like how endo and exothermic is its own category of reactions. There's metatheses and then not metatheses. And I think there's actually a technical term that I'm just forgetting. But we have a model for tracking the exchange of electrons between elements in a specific compound. And that motto is Leo the Lion says Gur. Of course, this translates to lose electrons, oxidation. If we see that an element from the reactant to the product form of itself has a increase in oxidation state, therefore signifying a loss of negative electrons, we would say it has been oxidized. And then on the other flip side, we would say gain electrons, reduction. So if an element from reactant to product form seems to have an decrease in oxidation state, therefore representing a gain of negative electrons, we would say it has been reduced. Therefore, together with the reduction in the oxidation, redox, we see that we have an exchange of electrons. So what are these oxidation state in numbers? Well, they are bane of your existence because you have to be able to compartmentalize how they're not formal charge, but they're written like formal charge, but they have their own rules. And they're still kind of a fake charge often, but sometimes they cross over with an actual charge, right? So this is weird category of identifying and characterizing an element in a compound. So what we would say is that the actual definition for oxidation state / numbers is that they're real or apparent, like or fake, charge of an atom or ion when all the bonds in the species is considered, oops, I think I meant to say are considered ionic. So it's like we treat every single bond, whether it's ionic or not, as if it's ionic, as if every element carries a charge. Okay. So these are the rules. Don't forget, the higher the rule, the more priority. And actually, it's not even necessary priority. It's just like I would start here. Like you start with the top rules. See if you can find any element within a reaction that actually satisfies the first rule. If you have a free element, give it a 0. Just like start there. Start with rule number 1, right? Rule / row number 1. And then you have the following rules, okay? A lot of you guys on the previous exam for 2002, you forgot that there is some fine print when it comes to oxygen that you're going to have to memorize, and hydrogen, where you see a charge that isn't the standard rule, okay? But you'll get it. So go ahead and I'm going to actually let you guys try this out on your own for pre-lecture. Go ahead and, well, actually, I'll do the first one with you and then you can do the second one. That's what we'll do. So for the first one, what you'll notice is that we have rule number 1, okay? All elements in their elemental form are 0. So that means any pure metal or any diatomic. And there are some allotropes like P4, okay, and like S8. There's some allotropes of non-metals that you're not diatomic, but they're the same element just bonded to itself, those are also 0. So what we see here is rule number 1. I already see that strontium metal and iron metal, okay, apply rule number 1. Rule number 2, any monoatomed ion has the oxidation state that is equivalent to its charge. But of course, remember that when we write oxidation states, it is sign and the number for oxidation state. Charge is number then sign. So just keep that in mind, but pretty much the equivalent magnitude. So what we see is we have 2 ionic compounds, both one in the beginning as a reactant, one in the end. By the way, this is definitely a single metal displacement. A single metal displacement reaction. So I would say for this one atomed ion, iron, let's start with bromine, because iron is technically a transition metal, which means its charge can change. So I'm going to go based off of the anion. Each bromine carries a 1 minus charge. Therefore, each bromine must be carrying a -1 oxidation state. And since there are 3 bromines, that tells me that the charge of iron must be positive, or 3 positive, and therefore its oxidation state must be on +3. Okay. Remember that the sum of the oxidation states should be equal to either the polyatomic charge or the overall charge of the compound. Kind of goes hand in hand. So what are then the oxidation states regarding each element? Iron is a +3, and each bromine element is a -1. Be careful not to take the sum of your ion charge when trying to figure out another ion in a bond and put that as the oxidation state of the single element. Okay, we still want to isolate the single element's oxidation state. All right, so and then we move on to the product side. Okay, strontium and bromine. Again, we have strontium, which is totally a transition metal. So we're going to have to go from the anion first. We know that each bromine is a -1 oxidation state because it has a 1 minus charge. And there's 2 of them, which means that my strontium must be a +2 oxidation state. So when I write the oxidation states, strontium is +2. Each bromine is -1. Okay. And what I see is strontium goes from 0 to +2. It's increased oxidation state. It's lost negativity. So if you lose electrons, you have been, Leo the lion says, oxidized. You have undergone oxidation. And then what we see is iron goes from +3 to 0. So what we would say is we have been reduced because our oxidation state is lowered. It's like we've gained negativity. We've gained more electrons. So we would say it has undergone reduction or has been reduced. For AP questions, please make sure when they ask you to justify your identification of redox that you actually talk about the oxidation numbers. Don't just say, oh yeah, this has been reduced, this has been oxidized. Show the work. That's where a lot of people lose points. So go ahead and try the next one. This one's not as simple because you don't have ions. So you're gonna have to dip into some of the other rules. And then pause me and resume when you're ready. All right, so hopefully you got the following answer. Notice here, chlorine Cl2O5 is a little interesting because we do use the rule where oxygen is almost always a -2, therefore determining that chlorine, despite being an electronegative atom, will actually take on a more positive aspect under this fake kind of ionic characterization known as oxidation states. So, yeah, but let's talk about now balancing half reactions. Oftentimes when we do redox, we often want to show specifically and isolate which species is being oxidized, which species is being reduced. And what that really means is we really want to track, well, how many electrons are being transferred between each species. Okay. So let's say we have a reaction where H is reduced from an oxidation state of +1 to 0. And C is oxidized with its oxidation state going from 0 to +2. All right. So how would we write this? Well, half reaction wise, let's write out the first reaction. So let's do the reduction first. We see that H is reduced. So it goes from H +1 and it gains an electron and it goes to H2, 0. Okay. And then we say for the oxidation half reaction, we have carbon, which goes from a state of 0. So this would be carbon solid, most likely. And what happens is it loses 2 electrons. So it separates. It's like 2 electrons are separated from itself. And it becomes carbon +2 and 2 electrons. So when we write the half reactions, then what we do is when we try to write the net balanced, electronically balanced reaction, and we have to do a little bit of multiplication and summation. So we know that if this is within the same reaction, and I know that I'm exchanging 1 electron from the particular hydrogen in a particular bond and 2 electrons from a carbon in a particular bond, that the exchange of electrons must be equal, right? I can't just magically gain 1 electron and lose 2 somehow. So what I do is I balance my half reactions via electrons, okay? Electronically balance them by multiplying this whole reaction by 2. So that when I multiply by 2, I get the following adjusted balance reaction. Okay. And actually, I shouldn't have written H2. What that really looks like is, 1 second. I shouldn't have written H2 because it's supposed to become H2. Apologies. I gave this answer away early on. Okay, it becomes this. And then what you see is you see that the 2 electrons lost are cancel out the 2 electrons gained. So when you sum up the redox for a full net balance, right? And I'm actually writing the full net balance redox reaction, is I get 2 H plus ones in some particular bond react with a carbon, 1 carbon in a 0 state, oxidation state, probably a solid then, to produce 2H0. Well, 2 H's to have a zero oxidation state would actually be H2, right? It's elemental form. And some carbon with a +2 oxidation state in some bond. And that would be my net balanced ionic equation, right? I'm only addressing the elements that actually matter, that are undergoing a oxidation state change. And I am making sure that the electron exchange is truly balanced from redox to oxidation half reactions. What we're going to talk about is in class, how do we consider the actual conditions that this redox is happening in? Because also when we look at this, right, like you have seen other problems where you've asked me, wait, this carbon is in a bond with O, but then it's not in a bond. Do I count the O? Do I not? How do I balance it? We're going to start looking at the method of how we add and account for other elements that the particular redox elements are engaged with in various conditions, both acidic and basic. But that's a kind of our review. If you feel a little bit unsure about your redox rules, There is plenty of practice problems in the workbook on like the first page to help remind you guys how to do reduction and oxidation assignment. So best of luck.